Hello again. Uh, Last time we have almost finished dynamic logic example. For the dynamic logic, we had like two major problems, as you may remember. The first problem was clock speed should be higher than the input's frequency, or input should not change during the evaluation time. And the second thing is that when you connect these dynamic logic in cascade, it's problematic. You should either use MP domino or you should use domino logic where you connect dynamic and inverter. And for this inverter, you can use a simple CMOS inverter, by the way. You don't need to make it also in dynamic logic. It can be a simple CMOS inverter. So let's try to implement a logic function by using dynamic logic. So the same story, you know, ORs are treated like parallel connection, ANDs are treated like series connection. So this is for the pull down network. First of all, we have to put the pull down network. A and, so A should be here. B or C and D. So please remember that if we do not show any arrow in transistor drawings, this means that this is NMOS. So even if I cannot put, even if I don't put any arrow in here, you should treat them like NMOS transistors. So this is the pull down network, and I have to implement the clock signals. So the upper clock transistor PMOS in here. This is output. And another clock signal in here. Clock and clock located in here. When clock is low, the bottom one is not connecting. When clock is high, the upper one is not connecting. And therefore, you can have the function. And this part is the pull down network. Exactly the same as CMOS implementation, of course, and part of it, or NMOS implementation. Okay, and this inverting operation is coming by default with this implementation. So it looks similar like this, quite similar to this one. So we have the pull down network, clock signals, and the output is defined. So we complete almost all the logic families. The last one is pass transistor logic. It's a bit different than the others because, you know, for the pass transistor logic, you may not need to use VDD or ground in some cases. Let's see how it works, but before then, let's try to understand the operation of a transistor as a switch. Assume that this is an NMOS transistor. Okay, so this transistor is operating like a switch between input and output, and this is the control signal. So what you expect from a switch? Of course, we have two expectations. The first thing is we want 0 voltage drop across input and output when control is high. And the second thing is we want zero current between input and output when control is low. So these are two basic things you want from an ideal switch. Ideal switch should be a perfect short circuit when the control is high, and it should be a perfect open circuit when the control is low. So we want to analyze this thing, how good an NMOS transistor as a switch. And before doing that, let's remember this ID/VDS curve. It's very important for us, okay? So it's very useful curve. You can utilize this thing in many different applications. Try to understand it very well. If you understand it very well, this means that everything will be quite easy. So this is a typical characteristic. So this is like linear region, this is saturation, and these curves are increasing as VGS is increasing. And also remember that this control is a digital signal. It's going to be either low or high. Low means 0 volts, high means 5 volts or VDD, whatever it is. So in that case, you don't need to worry about this, curves in between. When the control is low, so this is for control low, transistor is off, ID is equal to 0, which means that you satisfy this second condition. And this highest curve, let's say for VGS is equal to VDD or the control voltage. So at this point, it is important to find this VDS voltage drop, because depending on where are you operating on this curve, the quality of the switch changes. If you are operating somewhere in here, then we are in trouble because the voltage drop will be very high. But if you are operating somewhere close to here, then this is a good thing. The switch is like a perfect short circuit when the input is high. So it determines where we are locating the transfer function. So let's think about this case. When you apply high input, what's going to happen at the output? And assume that at the output we have a capacitor. Assume that the capacitor charge or the voltage at t is equal to 0 minus is equal to 0 volts. The transistor is not charged. So let's try to understand the transistor operation and the final voltage across the capacitor. And always keep in mind that ID/VDS curve is, as we have discussed in the previous part. The first thing that you should decide on here is nodes of the transistor. This is of course the gate, but what can you say about this node and this node? Which one should be source, which one should be drain? I keep telling you that a MOSFET is a symmetric device. Drain and source can interchange depending on the circuit potentials. So the circuit connection determines your source and drain. This node, for example, can it be source? I guess no. Why? Because then the voltage drop across here will be equal to 0. The transistor will be off, and you won't observe any conduction, and the capacitor cannot discharge in that case. But this is not true. Why? Because if this node is drain, if this node is source, then initially you have some voltage drop across gate and source. Because of that, VGS is larger than the threshold voltage, and you start conducting through this path, and therefore this node should be drain, this node should be source. in that case you have some VGS voltage, and VGS at 0 minus is VDD. So at 0 minus we are operating on this line. VGS is equal to VDD, and VDS is equal to VDD as well. VDD. So this is at T0 minus. But now we have some current, the saturation current through the transistor, and you start charging up this capacitor, which means that this voltage is increasing, which means that gate to source potential is decreasing. So you start moving on another line as T goes on. So VGS is decreasing, and because of that VDS is decreasing, the next time you are operating in here. If you continue, VGS continues to decrease because capacitor is charging up. VDS is also decreasing, and this will continue until some point. So this is as time goes on, CL is charging up. So during this time, of course, VGS is decreasing, VDS is decreasing as well. And this thing will stop, the current will stop when the ID will be 0, when VGS becomes VTN. Okay, when VGS becomes VTN, the transistor gets into cutoff, no current passes through CL, and that's the final capacitance voltage. So this thing will continue until you hit the cutoff state. So this is final curve, and this is gonna happen when VGS will be equal to VTN, and at this point VDS will be equal to VDD minus sorry, did I make a mistake? Yeah, I guess so, the VTN. So this will be equal to VTN, so which means that V out final can be VDD minus VTN. Okay, so let's repeat it once again. Initially the transistor is on, the current is high, and it's the saturation current with VGS is equal to VDD. As VGS decreases down, this current decreases as well, and you start operating on different curves for the NMOS transistor, and your VDS voltage is changing in this direction. And when VGS becomes VTN, the transistor gets into cutoff, no current passes, and this point is the final voltage of the output capacitance, and this corresponds to VDD minus VTN. What does this mean? This means that NMOS transistor is a bad switch for connecting high input voltages. So if you have high input voltage in here, the output will be high, but it's a bit lower than the input. So remember the first case that we are looking for. We want 0 voltage drop across input and output when control is high, and this NMOS switch does not provide it. So as a moral of the story, I can say that NMOS is not a good switch for transferring high inputs. So let's take a look at another case. When the input is low, maybe I can show it in here with a different color. Now let's change the situation. Now we apply low input or 0 volts. Again, let's decide on which part is gate, which part is source, which part is drain. So assume that V of CL at 0 minus is VDD. Let's assume that initially it's charged because we want to transfer 0 volts to the output. So in that case, this node will be source, this node will be gate, this node will be drain. And please note that for this configuration, VGS is VDD and it is constant. It is not changing with discharging of the load capacitance because source is now connected to the input. So we are moving on this line. Initially, the capacitor voltage is VDD. Okay. As the capacitor discharged with this current, we are moving on this line. The capacitor discharges, VDS decreases, transistor current is constant for a while, but then the transistor gets into linear region. Current drops down, but still the capacitor discharges. And when the current is equal to 0, you hit this point. This is final voltage. VDS is equal to 0, which means that Vout is equal to 0. Look at this case. You have input low and low input is perfectly transferred to the output. So I can say that NMOS is a good switch for transferring low inputs. So when you are transferring low input to the output, you don't have any voltage drop, you don't lose any voltage level. But when you are transferring to high input to the output, then there is a potential drop like VTN between input and output. So if you want to transfer low inputs, you can prefer NMOS as a switch. Let's take a look at PMOS. Similarly, in this case, assume that we have a PMOS switch and this is my input, this is the output. For case 1, you have a load capacitance, okay? So this is control. Case 1, input high and VCL of 0 minus, assume that 0 because I want to transfer this high to the output. So you have 0 volts in here, this part. You have high voltage in here. We have VDD and 0 volts in here. So this is gate. Which one will be the source or drain? So is this going to be source or this is going to be source? To turn on the switch, you have to apply low voltage at the control, right? Or 0 volts at the control because this is PMOS switch. To turn on the switch, you have to apply low at the control. So in that case, this node will be the source, this node will be the drain because you have VSG of VDD. So VSG is equal to VDD and this is constant during the operation. And again, we are operating on this line, ID versus VST. Initially, this is VDD. This line is for VST is equal to VSG is equal to VDD. We start from here. As the capacitor charges up, VST decreases. After a while, the transistor gets into linear, and this is the final point, final steady state. And this means that V out is equal to VDD. Look at it. Unlike the NMOS switch, PMOS transfers high input very well to the output. So this means that PMOS transistor is a good switch for transferring high input to output, which is a good thing. So let's take a look at case 2. Input is low. VCL of 0 minus is, let's say, VDD. We want to transfer low to the high output. So in this case, drain and source will change, of course. Again, the control will be low because you want to turn on the switch, of course. And this node will be 0 volts. This is 0. And this is initially VDD. Now, this will be the source. This will be the drain. Otherwise, you cannot set the correct parameters for the transistor operation. And now, as the capacitor discharges, VGS voltage is changing. Like in the NMOS case, if you draw ID-VDS curve, ID-VST, let's say, this is your initial point. You start from here for VSG is equal to VDD. But with the capacitor voltage or with the VST voltage changing, your VSG is changing as well. So next time you're operating somewhere in here. Next time the point shifts on left and bottom and you start moving on a different curve. And at the final point, when you reach ID is equal to 0, VST will be equal to VTP absolute value. So V out final will be equal to VTP voltage. It's not equal to 0. So PMOS transistor is not a good switch for transferring low input to output. So that's a bad thing. In fact, this makes sense. Remember this CMOS structure. In CMOS, we always use PMOS at the upper part, NMOS at the lower part. Why? Because PMOS transfers high better. PMOS transfers VDD better to the output without any voltage loss. On the other hand, NMOS conducts low voltage better, which means that it makes a good connection between ground and output without any voltage drop. It's going to be exactly equal to 0. So, it makes sense. In the CMOS, we utilize this switch property. So to summarize, NMOS, good for input low, bad for input high. PMOS, good for input high, bad for input low. And remember the CMOS characteristic, a typical CMOS inverter, like VDD. As you see, PMOS is good for high conduction, NMOS is good for low conduction, and that's why we always use NMOS at the bottom part, PMOS at the upper part. Please treat them like switches all the time, like this one. Okay. So what we are gonna do? We want some gate which conducts both high and low, right? You know, if you remember this previous slide, we want to make an ideal switch, and for the ideal switch, we want these two characteristics: 0 voltage drop across input and output whenever you have high or low input, and you want zero current. Having zero current is not a problem. Both of them provide zero current definitely at steady state, but 0 voltage drop is problematic. So by combining NMOS and PMOS in parallel, we can have this one. So as you see in here, PMOS in parallel with NMOS, this part conducts high better, this one conducts low better. So, you know, for any type of input, you guarantee that output will not have any voltage loss. And this thing is known as transmission gate. This is known as transmission gate. And sometimes people show it like this: input, output, control, and control. So this is exactly like a switch, nothing different than that. But the only idea in here is this: you want 0 voltage drop across input and output. Of course, this control and control bar, both of the controls should be applied in different way. If this is control, the other one should be a control bar. Okay, you don't need to, you cannot apply both controls to PMOS and NMOS because you want to keep them on at the same time if they are on. So this transmission gate, or either single transistors NMOS or PMOS, can be used for forming a logic function. So let's consider this particular case. You have A, and let's say this is output. When B is 1, let's say, output will be A, right? And no voltage drop across it because this will be 0, this will be 1. You conduct from here. For the other one, you are conducting from here. Output is equal to A. But when B is equal to 0, output is floating, which means it's not defined. It's like this: you have A and you have B control like this, and this is your output. If I can make another path in here, like this one, okay, let's say this is grounded, and let's say that B bar is applied in here, then what can you say about the output? Let's think about it. When B is equal to 1, output is A. When B is equal to 0, this is not conducting, this is shorted, and output is 0. So can I say that this output is in fact equal to A and B? I guess so, because the output is 1 only if both A and B are 1. If any of them is equal to 0, then the output will be equal to 0. Look at this structure, how simplified it is. I mean, you use only 2 switches. There is no VDD or ground other than the gate voltages. But you can form the logic function A and B. And transistor-wise implementation can be like this. B bar, A, and output. This is grounded. This will work like A and B. The problem with this implementation is since you are not using a transmission gate, there will be some voltage drop when the input is high because NMOS is not transferring high input very well. Other than that, it works very well. If you want to make sure that you don't want any voltage loss or voltage drop across high input, then you can add transmission gate. You can replace this thing, replace them by transmission gates to have no voltage drop. Okay, so this is for these two transistors. So we implemented an AND function without using CMOS logic, without using any supply voltage, or what we use is just the inputs and the ground. We didn't use any supply, so no supply required for this case. But one thing that you should be careful in here, you should check this floating case. You never leave the output floating at any time. To ensure that the output should be connected to ground or VDD with this extra connection, output should be always guaranteed to be not floating. Here is another example. As you see, we are using transmission gates in here. You can simplify it like this if you wish. So when B is equal to high, this gate is connecting. In fact, both of them can connect because you have high in here, low in here. So A is connected to Z. Z is equal to A. When B is low, okay, so in that case this will be low, this will be high, this pad is not conducting, only this pad and this pad are conducting, okay, Z will be A bar. This is another option to implement A and B, A-B function. So it will be like, this is like a multiplexer. So you have two pads, like this one, input 1, input 2. By applying B in here, B bar in here, Z will be equal to input 1 when B is high, input 2 when B is equal to low. And you can implement much more complicated functions by using this logic. This is a very good one to be used as multiplexer or MUX. But please keep in mind that things to consider: never leave the output floating. That's a critical thing. And also, you do not need to use VDD or ground. We do not need to use VDD or ground. Instead, you can utilize the inputs like we did in here. So test transistor logic is a very nice logic. It's like a puzzle solving, but sometimes it's very dangerous. You have to be careful during the implementation, and you have to check every single case one by one to ensure that the output is not floating at all. That's one of the common mistakes with the test transistor logic. When we ask the questions to implement A and B, for example, for A and B, they just draw this thing, which is of course not correct. So you leave output floating when B is low. So you have to put another path in here with B bar. And what you can do is you can connect this node to ground. If you do not want to use ground, for example, what you can do is you can connect this node to B as well. It will end up with the same function. When B is equal to 1, the output is A. When B is equal to 0, output is equal to B, which is 0, right? This also implements Z is equal to AB. And you don't need to use ground or VDD. You can just use the input variables like this smart way. Another example. So for the upper part, y is equal to, if b is equal to 1, it's gonna be A. If b is equal to 0, so if b is equal to 1, y is equal to A. If b is equal to 0, y is equal to b, which is equal to 0. So this is A and B function, exactly the same thing. Let's check this one. If b is equal to 1, output is, that is A bar. If b is equal to 0, z is equal to b, which is equal to 0. So I can say that this is A bar B. So it's really a nice example for test transistor logic. One critical thing is never leave the output floating. Another example in here. When b is equal to 1, z is equal to A bar. When b is equal to 0, z is equal to 1. Why? Because this is in fact B bar, which is 1, right? So I can say that this is the function of A bar, B bar. Let's check it. No, this is not exactly true. This is in fact A bar or B bar. Why? If B is 1, you should check A bar. If B is equal to 0, output is directly equal to 1. So this is a nice implementation of OR function, or implementation with PTL. So please check your textbook. They have some nice examples on test transistor logic. It's a very nice logic family to use in some digital applications. Okay, so we end up with this logic families part. So now we know path transistor logic, domino logic, dynamic logic. CMOS is the most critical one. That's the best one in terms of the others and most commonly used one. But dynamic and domino are useful for synchronization issues. If you want to synchronize your inputs and outputs, you need to use some clock signal, and dynamic and domino may work in that case. They also have zero static power consumption. Path transistor logic is an interesting one. It's like a puzzle. It's commonly used for multiplexer like implementations. Most common advantage is you don't need to use VDD or ground as an input or supply. Only the input potentials could be good enough to run this transistor logic. And if you want to use perfect switches with zero voltage drop loss, then you need to use transmission gates, which doubles the size of the path transistor logic, because you need to use 2 transistors for each individual switch. And if you do not have that much space on your IC, or if you are comfortable with this voltage drops, then you can utilize single transistor implementation for the switches. Okay, I'm gonna stop here, and next lecture we are gonna start with a new topic. I think it's gonna be ready by next Thursday.